Thomas?
How similar is this problem to yesterday's?
Very similar.
Very similar?
Yeah.
Okay.
And to tomorrow's.
Okay.
All right. What's the first thing we should do when we run this test? Nice, Jonathan. We will get to the assumptions for sure, but we should define the parameter. So good start. So write super small. Okay. Let P, right? What does P stand for? Population proportion. Population. Just think alliteration here. Population proportion, PP. All right? And for this case, we're talking about the proportion of children in the United States that have a congenital abnormality. So let P represent the proportion. That's not it. Proportion of U.S. children that have a congenital abnormality. For my anatomy and physiology people in here, what does that mean, congenital? Do you know? What did you just say? Boogers? Interesting. It's not what it means, actually. Say it again? It means something with together, right? Like, if you have something that's congenital, it means it was passed down to you from your parents. All right? So through the genes. Okay? So not congestion. You're welcome. I don't think you need to know that, but just in case you were curious what that means. All right? Yeah, it's good to know. Okay. Now, hypotheses are next. What are we assuming right now to be the best idea for the rate of children in the United States that have a congenital abnormality? 5%. So I'm going to put P equals 0.05. Right? What are we trying to prove for the alternative? That it has increased. Now, let's say tomorrow the question says, does this study show strong evidence that there is a difference in the rate? What are you going to put for the alternative symbol? If it just says difference, you're going to put not equal to. And I'll show you with our next one what that would mean. I'm not going to record it, but the backside, I'll show you what happens when it's not equal to. What if it said that it has decreased? Then that's going to be less than. So just make sure you're checking to see what that word is. That will tell you what symbol to use for the alternative. Questions so far? Now it's time for the assumptions and conditions. I'm not going to put the titles. I know I've been doing that every time. Like I put the title, independence assumption, then the statement. Then I put the randomization condition, then the statement. I'm just going to write the statements. All right. You can do that tomorrow to save time. You can do it on the AP exam to save time. All right. If you feel like you need to put the titles, go for it. It's not wrong. All right. So what am I assuming in terms of independence here for these children?
One child having a congenital abnormality does not have the chance of the next child having an abnormality.
Very good. I'm going to do a lot less words than that, but totally right. So one child having a congenital Did I spell that right? No, I spelled it wrong. Gosh. Congenital abnormality won't affect others. Any concerns here? No. I mean, there'd be one big concern if they're talking about sampling or looking at a study for children that are related in some way, right? That would be a worry. All right, but if it's just random and they're, not related, then I'm cool with it. Does it say that the 384 children are random? No. It does not. So remember that statement is these 384 children are a good representation of all children. I guess I should say all U.S. children. That's the randomization condition. When they don't say the word random, that's the statement you're going for. Okay? Next up is the 10% condition. Actually, this one is not big enough yet. We're going to get to it. And if you do the order, like if you do it out of order, it's fine, right? As long as you do it all, right? I don't care if the order is off. The next thing I'm going to do is just make sure that's not too big, actually. All right, so this is where I multiply the 384 times 10, which is 3,840. Are there more than 3,840 children in the United States? Yeah, way more than that. So our sample size is not too large. All right, so that finishes what I always think of as like my first column. Assume independence, check randomization, and check to make sure your sample size is not too large. All right, that's the 10% condition. Next is to make sure that it is large enough. So I always assume it is. So 384 children is a large enough sample. All right, and now this is the one difference. So Leslie, when you were watching the stuff from 19 to this chapter 20, there is a difference here with the success failure condition. So this is where we did n times p and n times q. All right, so for the confidence intervals, we would just use 46 as the number of successes, and that, 38, don't do the math there, right, for failures, right? But we don't do that for tests. For tests, we take the sample size and we multiply it by this proportion, all right? So this from the null hypothesis. So 384 times 0.05, and then 384 times 0.95. And, just to be clear, I know I'm saying a child diagnosed with a congenital abnormality is a success. I would argue that is not true, right? But for this problem, it is. Okay? So who's got 384 times 0.05? 19.2. 19.2. So this one is 364.8. Both numbers are 10 or higher. All right, so our sample size is large enough. All right, so now we're ready for our statement to explain what we're going to do. The conditions have been satisfied. So I will use a normal model to run a one proportion z-test. I am going to give you the formulas tomorrow for the quiz. You're not going to get the formulas for the test. All right, but you'll get it tomorrow. All right, we're going to calculate the z-score. So I'll write it down for you. P hat minus p over the standard deviation of p hat. All right, I know many of you already know the standard deviation of p hat formula. P times q over n, the square root of all of that. You know what I forgot? I'm sorry about that. I missed a line, so I'll put it here. So it was, our sample size is 384. Our number of successes was at 46?
Yeah.
46. So p hat is 46 over 384.
One,
120. So approximately 12%. All right, so now I'm going to take my specific statistics from this study, put it into the formula, and then go to the calculator to find the z-score. And then also don't forget you have to find the p-value. Do you guys remember the thing that I check when I write down my formula here to find the z-score? Can you say which ones you're right? I do. Very good. Right, these should match. So good job. That's always a good check. And if you know to do that, that should help you tomorrow on the quiz. Somebody was next. Tomorrow on the quiz, if you need help with the button pushing on the calculator, I will help. All right, but don't get used to that, right? I'm not going to do that when we take our test over this. Okay. All right, you guys ready? Let's do it. Okay, so we're going to do stats, over to tests. The only test we know right now is the one proportion z-test, which is number 5. So you use that tomorrow. Our population proportion, so the best idea of what's going on out there in the world for the rate of children in the U.S. that have a congenital abnormality is 5%, so 0.05. They had a study of 384, that's my success dose, 384, okay. We found 46 out of 384 U.S. children had a congenital abnormality, or signs of one at least. Go to the alternative hypothesis if you forget, right? Go to the alternative. That symbol used is greater than. And click enter on that. If you click draw, it's just going to show you the curve, right, with the z-score. So you can do that if you want, but I always click calculate, and then I actually draw on my paper what it is. All right, so we got a z-score of 6.275. That is absurdly high, right? I usually expect my z-scores to be between what numbers? No, not 0 and 1.
1 and 2?
No.
1 and 3?
Think about when we draw the curve, right? How far do we go up? 3 standard deviations both directions. So usually I'm expecting my z-score to be between 3 and -3. So when I see a z-score of over 6, that tells me that that is extremely unusual. So I'm going to draw the curve, but really it's going to be difficult here, right? It should be like way over there, right? Super far to the right. And which way are we shading? Greater than to the right. So what is my p-value going to be before I even look at it? My p-value is going to be what? It's the area. So how much red did I just shade there? Tiny amount, very little amount. So this p-value I'm expecting to be minuscule, really, really tiny. Let's look at it. What is it? It's 0.00000, lost track, 0, 0, 0, 0, 1.
It should be 9.
I'm just making it up, right? The idea is that's essentially what?
Nothing.
Essentially nothing. So I write p-value is essentially 0. Okay? Now, tomorrow's quiz, it won't be that. Okay? But it's good to see an example like that so you're not confused. Because I get students every year, they're like, wait, I thought the p-value had to be between 0 and 1. That's true, right? It is essentially a percentage. So this is confusing, but notice that scientific notation, you're moving it 10 times to the left, right? So it's very, 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 very small, essentially 0. So guys, I told you yesterday that a p-value is a conditional probability, all right? So if I assume that the rate of children in the United States that have a sign of some type of congenital abnormality is 5%, and I go to this study and find out that 46 or more out of 384 have that congenital abnormality, the likelihood of that happening is essentially zero. All right. So since that probably will never happen, what's more likely is that this 5% is wrong. All right. And it's actually, it's something over 5%. So that's what we're going to write for our conclusion. All right. So with such a small p-value, I will reject the null hypothesis in favor of the alternative. Make sure tomorrow when you make your conclusion, right, that you don't stop here. You won't get full credit if you just stop here. Yes, you've made the right decision with a small p-value. With a small p-value, you reject the null hypothesis, but you need to put it into context. So I'm going to say that the rate of children in the United States that have a sign of a congenital abnormality is actually above 5%. I'll go back, don't worry. Uh-oh. I'm worried. Oh, no. There we go. Bless you.